Welcome back. Today we are going to talk about Boltzmann distributions and kinetic energy distributions. So we're just going to kind of talk about what happens to gases, or just particles in general really, when we look at the speeds. This shouldn't take too long. We're just going to be kind of looking at some graphs. Before we get to talk about this, we want to talk about absolute temperature. So absolute temperature is measured on a scale called Kelvin. 1 degree Celsius is equivalent to 1 Kelvin. Converting between Celsius and Kelvin is actually really easy. We just add 273 to whatever Celsius value we're given. So say, for example, we're at 0 degrees Celsius. That's the same thing as saying 273 Kelvin. They go up at the same time, too. So 1 degree Celsius is 274 Kelvin, and so on and so forth. The Kelvin scale is based on molecular motion. When we're at 0 Kelvin, that means we have no particle motion at all. This is referred to as absolute zero. We actually can't get lower than this. It is the absolute bottom floor. We cannot have a temperature value that is lower than 0 Kelvin because there's just no more particle motion. So how can there be anything lower than that if they're just standing still, right? If you double the Kelvin temperature, you will double the molecular motion. So it works, it's a 1-to-1. It works just the same. So at any given temperature, all particles present move at a variety of different speeds. Depending on their size, depending on the energy that they have. And this is often determined through what we call a Boltzmann distribution. So a Boltzmann distribution is a graph. We are going to want to draw X and Y axes for this. Give yourself a little bit of space. Don't take up the whole space. Maybe like half of it, because we're probably going to draw 2 of these underneath this little blank. So I'm going to come back after I draw some axes. You go ahead and do the same. This is our Boltzmann distribution axis. On the y-axis we have the number of particles, and then on the x-axis we have speed. So we're analyzing the number of particles and how fast they go, or how fast those particles go at a certain speed. You know, things like that. Now, usually a normal Boltzmann distribution will look something a little bit like this, where it'll start kind of somewhere, not at 0, but kind of a little bit above. And it does kind of a little bit of a loop. I got to back that up a little bit. Kind of like this, and then it'll go down and kind of peter off. That would be like a normal Boltzmann distribution, and it depends on what we're measuring. So let's say, for example, this is at 20 degrees Celsius. So what this Boltzmann distribution says, let's just look at a couple points. Say, for example, if I'm looking at this point here, kind of towards the center, what I'm saying is that there are not a lot of particles that move at a slow speed, and that also over here, I have not a lot of particles that move at a really fast speed, but most of my particles are moving at a pretty average speed, about 20 degrees Celsius. Now, I could change this graph depending on the temperature. Let's say, for example, that I increase the temperature. What do you think is going to happen to the graph? Well, if I increase the temperature, the graph is going to stay pretty relatively the same, but I'm going to have a greater distribution of gases that are going faster. So my graph is going to kind of flatten out. It's going to change its shape just a little bit. Now understand that a Boltzmann distribution is a calculus-based graph, meaning that if I take the area of the curve underneath the line, I can have the number of particles. That means that the distribution underneath the line has to be about the same. So you want to make the point being is that you want to make the shape of your curve kind of the same either way. Similar is what I should say. This is about 50 degrees Celsius. We're just kind of estimating. What happens if we cool the temperature off? Let's say, for example, that we cool the temperature down, maybe like down to 0 degrees Celsius. My Boltzmann curve is now going to, probably not as bad as that. It's going to flatten out kind of closer towards the middle here. Hold on, I'm getting it. There we go, something like that. So if I have it, it's going to take a second. It's catching up with me. But if I decrease the temperature, the thing that I would expect to see is less particles moving at a faster speed. So here we go. Here's a line where maybe we're at like 0 degrees Celsius. So now I have a larger distribution of gases that are moving at a slower speed as opposed to a faster speed like in the other graphs. And that's really all a Boltzmann distribution shows. And we can also relate this, if we kind of go a little bit further, we can also relate this to particles not based on temperature, but also based on size. So if you just make yourself like another little graph here, And we do the same thing, right? We have speed and we have particle numbers. If I had, well, let's kind of figure it out here. Let's say that I have three gases. I have helium, I have neon, and I have argon. And I were to draw the three lines for each one. Let's say that I have one Boltzmann distribution that, we'll use the same distributions, kind of like we used before. If I have the same distributions that I had before, similar shapes and similar areas under the curve, then which one of those gases would belong to which line? Meaning that at the same temperature, which one do you think is going to be moving faster? Well, based on what we talked about before when we discussed kinetic energy, larger things need to move slower because they're just going to move slower. At same speeds, they're going to move slower. So argon is probably going to be the green arrow because it is the slower one. Neon is the one that's in the middle because it is it's not the smallest, but it's not the largest. Helium is going to be moving the fastest because it's the smallest. So we could use Boltzmann distributions for this as well, like if we're just looking at things that are at equal temperature. So in the consideration of kinetic energy, we have another curve called the kinetic energy distribution curve. And this one we can draw kind of large. We only need one graph for this. But if I have an axis, just like we had before, where we have number of particles on the y-axis, and you can probably imagine what we're going to measure on the x-axis. We're not measuring speed this time. We're measuring kinetic energy. So if I had kinetic energy in the number of particles, based on the temperature, I can look to see the kinetic energy that's involved. And remember, kinetic energy is measured as 1/2 mv squared. So if I just had sort of a general kinetic energy distribution curve, it's very similar in its structure to the Boltzmann distribution. Let's say that this is about at 20 degrees Celsius. We're just measuring different things. So in this situation, we're measuring the kinetic energy present at 20 degrees Celsius. We're saying that a large distribution of our particles have about a middle amount of kinetic energy at 20 degrees Celsius, but not many of them have less or more than that. But if I were to increase the temperature, I would notice a very similar pattern as I saw before, where the area of my curve would change and I would kind of flatten it out, meaning I would have more particles in the higher range than I do in the lower range than I did at a lower temperature. And that's pretty much it. So these are just graphs that we're going to observe. We're not really going to be there's not a math part to this. It's not like we have to find an equation to create these graphs. The takeaway here is that, say for example, if you were given a problem that said like draw the Boltzmann curve for these two different gases at these two different temperatures, you would just make sure that the higher temperature has a wider curve than the lower temperature, which will have a more narrow curve at certain locations. That's really the takeaway here. So we will continue next time by talking about solids. See you then.